Hey everyone, and welcome. Today we're going to deconstruct Kubernetes. If you've ever looked at it and wondered how it juggles thousands of containers without breaking a sweat, you are in exactly the right place. We're going to break down the absolute core building blocks that every single developer needs to master. We're talking running your code, connecting it to the world, storing its data, and of course, keeping its secrets safe. Let's get right into it.
Spinning up a single container, that's the easy part. But what happens when your app grows and you suddenly need to run hundreds or even thousands of them? How do you push updates without taking everything down? How do all those little containers talk to each other? And how in the world do you scale up when traffic spikes? And that's the exact problem Kubernetes was born to solve. It's the orchestrator, and today we're popping the hood to look at its most essential parts.
So first things first, let's talk about workloads. This is all about how Kubernetes actually gets your application's code up and running. And spoiler, it's not as simple as just starting a container. Kubernetes uses these really powerful controllers to manage the entire lifecycle of your application, making sure it's always running exactly how you want it to.
Okay, so the one you're going to see 99% of the time is the deployment. You can just think of this as the absolute workhorse for your stateless applications. Things like your web servers, your APIs, any service that doesn't really need to remember its own unique state. You literally just tell it, hey, I want 3 copies of my app running, and the deployment controller just makes it happen.
But here's the magic, right? The reason deployments are so powerful is all about how they handle updates. They use this brilliant strategy called a rolling update that gives you 0 downtime. So instead of just killing all your old pods at once, Kubernetes smoothly brings up new pods with the updated code while, at the same time, gently taking down the old ones. And if something goes wrong, no problem. It keeps the old version on standby, ready for a super fast rollback. It's an absolute game changer for keeping your app online, for sure.
Okay, so deployments are your go-to for stateless apps, where any pod is basically a clone of another. But what about the tricky stuff, like databases, where each instance is special and has to hold on to its own precious data? Well, for that, you need a StatefulSet. And the crucial difference here is that a StatefulSet gives each and every pod a stable, unique name and network identity, and it guarantees that its storage follows it around no matter what happens.
And then there's this other really cool workload, the DaemonSet. Its job is simple but absolutely critical. It makes sure that one copy of a specific pod is running on every single node, or maybe just a few specific nodes in your cluster. This is perfect for all those background infrastructure tasks like collecting logs or monitoring server health. It's basically the run-everywhere controller.
So, to wrap this section up, let's just do a super quick recap. You're going to use deployments for your everyday stateless apps. You'll reach for StatefulSets for things like databases that need a stable identity. And you'll use DaemonSets for those critical node-level agents. Just knowing which one to pick is really the first big step to mastering Kubernetes.
All right, so our app is up and running. Awesome. But how does anyone actually talk to it? And just as important, how do our different microservices talk to each other? Well, that brings us right to our next section, networking in Kubernetes. So the most fundamental way to connect pods is with something called a service. And the default type you'll always get is a ClusterIP. What this does is it gives your group of pods a single stable IP address that only exists inside the cluster. So if your front-end service needs to call your back-end API, it just talks to that one stable IP, and the service handles load balancing the request to a healthy back-end pod. You can think of it like the internal switchboard for your whole application.
Okay, but that's all internal. What if you, from your laptop, need to access the application from the outside world? The next step up is a NodePort. This service type takes your internal cluster IP and also opens up a specific port on every single one of your servers or nodes in the cluster. It's a super handy, quick and dirty way to get traffic in, which makes it awesome for development and testing.
But let's be real, NodePort has some problems for production, right? You have to know the IP address of one of your nodes, and what happens if that specific node goes down? For real-world production traffic, you need something way more robust, something with a single, stable front door for your application.
And that, my friends, is where the LoadBalancer service comes into play. This is the solution you use in production. When you create a load balancer service in a cloud environment like AWS or Google Cloud, Kubernetes talks directly to that cloud and says, hey, build me a real external load balancer. This gives you a stable public IP address that routes traffic into your cluster, making your app highly available and ready for the world. All right, so let's lock this in. Use ClusterIP for all your internal service-to-service chatter. Use NodePort when you just need quick external access, maybe for some testing or a demo.
And for your big production applications that need to face the public internet, LoadBalancer is absolutely the way to go.
Okay, so we can run our code and connect to it. But here's a big gotcha with Kubernetes. Pods are meant to be temporary. They can vanish and get replaced in the blink of an eye. So what happens to the data? How do we make sure our critical information actually survives? This brings us to our next crucial topic, persistent storage.
The first piece of the storage puzzle is the persistent volume, or PV. The best way to think about this is as the supply of storage that's available in your cluster. It's a chunk of storage, maybe a cloud disk on AWS or a network file share that an administrator makes available. The key thing here is that the PV exists totally on its own, completely independent of any pod's life or death.
Okay, so if the PV is the supply of storage sitting there, the persistent volume claim, or PVC, is your application's demand for it. This is how your application asks for storage. A developer just creates a PVC that says, hey, I need 10 gigabytes of storage that I can write to. They don't have to worry about the details of where it comes from, they just make the claim.
So how does this actually work? How do they find each other? Well, it's a pretty simple four-step dance. First, an admin provides the storage, the PVs. Then, a developer requests that storage with a PVC. Then Kubernetes plays matchmaker. It looks for a PV that meets the claim's requirements and binds them together. And once they're bound, your pod can finally mount that PVC and start reading and writing data that will actually stick around.
All right, here's a little pro tip, something a senior engineer absolutely needs to know. What happens when you're done with the storage and you delete your claim, the PVC? That's all controlled by the PV's reclaim policy. Retain is the safest for production. The actual storage disk is kept until you manually clean it up. Delete is super convenient for dev because it just automatically deletes the underlying cloud disk for you. Choosing the right policy here is critical for not accidentally deleting your data. Okay, we're almost there. We can run our code, connect to it, and save its data. But what about the really important stuff? The passwords, the API keys, the database credentials. Managing secrets is one of the most important parts of a secure system, and our final section is going to cover the modern way to do it right in Kubernetes.
Now, you could use Kubernetes built-in secrets, but honestly, the modern, best practice way is to use a real, dedicated secrets manager like AWS Secrets Manager or HashiCorp Vault. And the bridge that connects that secure vault to your cluster is the External Secrets Operator, or ESO. It's this powerful little tool that runs in your cluster, connects to your external vault, and automatically syncs secrets into your cluster so your app can use them safely.
And the way it works is just so elegant and simple. First, you install the operator. Then you create a special secret store that just tells it how to connect to AWS. Then, for every secret you need, you just create an external secret object that points to it. ESO sees that, goes and securely fetches the secret from AWS and creates a regular Kubernetes secret right there in your cluster for you. It's all automated, all declarative, all secure.
And why go through all this trouble? Well, the benefits are massive. You're handing off the really hard security work to a service like AWS. You get incredibly fine-grained access control using their IAM policies. You can even get things like automatic secret rotation. It gives you one central, secure place to manage all your secrets, which is just a huge win for security and for your sanity.
And there you have it. Workloads to run your code, services to connect it, volumes to save its data, and external secrets to keep it all safe. These are the fundamental pieces, the map to the entire Kubernetes landscape. So now you have the map. The only real question left is, what amazing thing are you going to build with it? Thanks for joining this explainer.